Now, there's a special case for Snell's law, and it goes by the name of total internal reflection. And what happens is if we go from a high index of refraction material, such as water, we go to a low index of refraction, such as air, that the light at special cases or at a certain point is not going to be able to bend far enough in that material. So what will happen is the light's going to try to bend from the water to the air. It's going to actually bend further away from the normal, but it's not going to be able to. And a special case will show up, and that's called total internal reflection. As we said, with Snell's law, there's a special case when we go from a high index of refraction to a low index of refraction of medium. We're going from water into air, so high into low. What happens is as we start to increase the incident angle, we'll notice that the refracted angle is a greater angle. There's a lower index of refraction in the refracted material in the air, which means that there has to be a higher angle. And at some point, the closer we get to this kind of special angle, we're going to call it a critical angle, the closer the refracted light gets to 90 degrees, to the point where when we're sitting around, for this case, about 47 degrees for the incident, that there becomes no refracted angle. And instead, all the light bounces off of the surface and becomes reflective. So you can see we just get a pure reflective beam, and the refracted beam, the one that would be in the air, just disappears. And the further I bend this, it doesn't ever come back. It just happens to reflect. The critical angle, anything above the critical angle will just have pure reflection. But the critical angle, the one that we solve for in many physics problems, is the angle when this first happens. So what is the smallest angle? So again, right around the 46, 47 degree mark. One of the most interesting uses of total internal reflection is that of fiber optics. We use fiber optics in communications all over the world. But we take the light, we send it down a piece of glass, and the light tries to leave the glass. It goes from a glass to air interface, but since we're above the critical angle, the light cannot leave the glass. So all it does is bounces internally down the length of this fiber optic, and that's how we can communicate a signal. We pulse the light, and it travels down the piece of glass.